Hello learners, welcome back to the series of lectures on functional analysis. In the last lecture, we saw lots of examples for non-linear spaces. Today, we are going to see how to get more non-linear spaces out of a given non-linear space. Well, so we will have X to be a non-linear space. So, I will use NLS, a short form for non-linear space. Now, so that means what? This pair, this is the non-linear space. So, you have this pair. So, this is the non-linear space. Now, if Y is a subspace of X, a subspace, by a subspace I mean a vector subspace, a subspace, then what you do is you need a norm on Y. So, what we are going to do is that we are only going to, so this is defined as, just take the norm on X, restrict it to Y, right. So, that means for Y in Y, norm Y is defined as, look at this element Y as an element of this space X and then take its norm. So, then this Y with respect to this norm is again going to be a norm linear space. Right. A simple observation here is that, so if you have Y subspace of X, right, which is a subspace, you have a subspace, right. Now, look at Y closure of Y, this is in fact inside X, fine. So, first claim is that this Y closure is also a norm linear space. In fact, not only that, well, so first thing what you need is that not only that it is a norm linear space, first thing what you need is that this Y closure should be a subspace. So, the procedure whatever we have done here, once we show that this is a subspace, then it is enough, that much is enough, because this procedure whatever we have said, that will help us in showing that this is a norm linear space. Well, so to show that this is a subspace, what we need are the following, that it is closed under addition and it is closed under multiplication or scalar multiplication. So, choose X and Y from Y closure. From the classical real analysis or from the theory of metric spaces, which you have done in your previous semesters, you must have learned that there exist sequences X n and Y n in fact they come from Y such that X n converges to X and Y n converges to Y. In the first lecture, if you remember right, we saw that addition and scalar multiplication, they are in fact jointly continuous, that much we saw. Therefore, these two together will imply that X n plus Y n will converge to X plus Y. Y n will converge to X plus Y. This is because of the fact that plus is jointly continuous. This much we saw in the first lecture, right. Now, this X n plus Y n, this belongs to Y because Y is a subspace. X n plus Y n, this belongs to Y as Y is a subspace. So, because all x n plus y n they all belong to Y and x n plus y n converges to x plus y, that tells us that this x plus y belongs to Y closure. In a similar fashion, similarly one can show that lambda y belongs to Y closure whenever lambda is a scalar and Y comes from Y closure. That is it. So, which means that we have shown that this Y closure is a subspace, and therefore, our previous construction will immediately tell us that Y closure is a norm linear space, right. So, now there are some interesting results for these closed subspaces. The first one is what is known as Ree's lemma. So, if you have a closed subspace of a norm linear space X, and if I have an element which is outside of X, what is the distance between X and Y? Well, that much is known to you all from the theory of metric spaces, but then given an arbitrary one that may not help us. The whole point that we wanted to insist here is that how close can we get an element of X, which is how close it is to Y. So, answer is provided by this lemma. So, let Y be a proper closed subspace of X, then for each R in the interval 0 to 1, there exists X R from X such that R less than or equal to distance between X and X R and Y, and it is also less than or equal to 1, and the norms of all these X R's you can very well choose it to be of norm 1, yes, because you do not have to worry about its norm because it is always going to be 1. So, that much you can always choose, right. Right. So, first thing, let us make a simple observation. So, let us fix. So, if you what we are going to do is that you fix an X and R in 0 1, right. In fact, not only that it is in X, in fact it is going to be, I wanted it from Y complement, that is the whole point here, which is X minus Y. In fact, let me write it, which is X minus Y, right, and you have a scalar in the open interval 0 to 1, right. The first claim that we are going to make here, or an observation, is that so once you have an element X and an R, there exists Y which depends on both X and R, right, that is what we wanted. This comes from Y such that the distance between, or the norm of x and this yxr, this is going to be less than or equal to distance between x and y whole upon r. Right. So, why is this observation true? Well, so let us show this by contradiction. Suppose that this is not true. Right. So, if this is not true, then we will have to end up with a contradiction. Let us see what it is. So, if this is not true, which means if you cannot find yxr, that means, so that means what? Let us write down norm of x minus y, this is always greater than distance between x and y whole upon r, and this is true for all y in y, right. So, how is this going to affect us? Right. So, this is true for all y. If you notice, your right hand side is independent of y, while the left hand side has got y. So, taking infimum over all y, this will give us that infimum over y in y, norm x minus y, this is going to be greater than or equal to distance between x and y whole upon r. Right. But we know this, whatever we have on the left hand side is the distance between x and y. Our choice of x is such that x is from the complement of y, and our assumption about y is that it is a proper closed subspace. Therefore, this quantity distance between x and y, it is a non-zero quantity. In fact, it is going to be strictly greater than 0, and therefore, you can divide both sides by distance between x and y, which will imply that 1 is bigger than or equal to 1 upon r. That means, r is bigger than or equal to 1, but then our choice of r is such that it is in the open interval 0 to 1, therefore, a contradiction. Right. So, you have a contradiction. So, once you have a contradiction, that means that this statement whatever we have made is actually true, right. Now, so once we have observed this one, now let us proceed further. So, how are we going to prove this? We wanted to make use of this, right, fine. So, for each r in 0 1, so we have already fixed x in y complement. So, choose yr, that is what the claim says, you can choose a y. Well, we have already, so we have fixed, so maybe I will write it as fix x in x minus y, then for each r in this choose yr in y such that the statement holds norm of x minus yr, this is less than or equal to distance between x and y upon r. Yes. So, this much is known to us, right, fine. Fine. So, once you have this, now what we, because we wanted something to be of norm 1. So, what we will do is, so let me choose xr, that is what we wanted, which is x minus yr upon norm of x minus yr. the way we have chosen XR tells us that it has got unit norm, right. Now, only thing that we will have to prove is this inequality, right. So, distance between XR and Y, the subspace Y satisfies this inequality, right. So, it lies between R and 1, yes, that is what we wanted. Let us go to that. So, our claim is the following. The claim is that R less than or equal to distance between XR and Y, which is again less than or equal to 1 for all R coming from the open interval 0 to 1, right. So, this is our claim. Now, let us go to one way is clear. Which way? The right hand side is clear. Well, why is it true? In fact, you observe that norm of XR, this is 1 and also 0 belongs to Y, right. Therefore, so if you look at, so distance between X and Y, which is the, by definition it is given in terms of infimum, therefore, this is less than or equal to norm of XR plus 0, right, because 0 is an element of Y. So, but XR plus 0 is just XR, but norm of this is equal to 1. So, this gives us one way inequality. Now, let us go to the other way. Now, on the other hand, we wanted the other way inequality. On the other hand, resistance between XR and Y, right. So, this by definition is by definition of XR, which is X minus YR upon norm of X minus YR comma Y, right. So, which is equal to 1 upon, I am just pulling this out, this being a scalar, I am just pulling it out, times distance between X minus YR, well, distance between X minus YR comma Y. Well, so this is going to be 1 upon norm of, let me write down, this is the, write down what this quantity means, distance between X minus YR and Y, infimum of norm of X minus YR minus Y, such that Y belongs to capital Y. Now, if you notice here, this YR, it is an element that we have chosen from Y, if you notice here, right. Therefore, Y minus YR, it is again an element of Y, so it does not matter. So, this is going to be norm of X minus YR times infimum of norm of X minus Y, such that Y belongs to Y. That is what we have. Now, we are almost done with what we wanted. The way we have chosen YR, that tells us that norm of X minus YR is less than or equal to distance between X and Y upon R. Now, what we have here, in fact, let me write down. So, this is distance between, what we have in the numerator is distance between X and Y, capital Y, upon norm of X minus YR, that is it, and we are done. So, this is going to be bigger than or equal to R. The way we have chosen our YR tells us that this inequality is true, and hence we are done, right. The next natural question that we would like to address here is the following, that what will be the interior of a subspace. So, if you have a subspace, what will be the interior? And before we speak about interior, the natural question that one would like to address here is that when is the interior non-empty? Well, when you want to speak about interior of a subspace, the first question that we would like to ask is that as a subspace of y or as a subspace of x, because when you want to speak about interior being a metric space, you can speak about it either as a subspace of x or a subspace of y, but the whole thing is that our interest is only with respect to x, right. So, let me put it in the form of a lemma. So, let y be a proper subspace of a non-linear space x, right. Then the interior of y, in fact this is with respect to x, is non-empty if and only if y is equal to whole of x, which means you cannot have a subspace whose interior is always non-empty. You cannot have any subspace, in fact that is the whole thing, unless and until it is the whole of x. Right. Well, let us begin with well, the easy part. Let me first start with the easy part, which is the backward part. So, if y equal to x, then the interior of y, which is same as the interior of x, but we know that interior of x is same as x itself, because that is the space that we are considering and which is always non-empty. That is it, done. We are done with one part. Now, let us go to the forward part. The forward part is again not a difficult one. So, suppose that interior of y is non-empty. So, we will have to show that y is equal to x, right. So, interior of y is non-empty, that means this implies there exists, you get a point y in y such that well, there exists y in y for which there exists r greater than 0 such that the ball with center at y and radius r is contained in y, right. This is going to be contained inside y. So, this is the crucial part, in fact. So, this is in fact contained in the interior of y, which in turn is contained in y, right. So, this is the most crucial part that we have observed. Well, why is this crucial will be clear soon. Now, what we wanted is that we will have to show that y is equal to x. We already know that y is contained in x. Only thing that is left to show is the other inclusion, that x is contained in y. In order to show that x is contained in y, it is enough to pick an arbitrary element from x and show that it is also in y. So, let us do that. So, let me choose an x from x, right. We have chosen an element, arbitrary element x from x. So, we will have to show that this element is also inside y, right. So, you have chosen. Now, let me define a new element x dash. How is it going to be? So, let me define it as r x upon 2 times norm x plus y. Well, basically what have I done? I have dilated this element x, or I have scaled this, and I have also translated it so that this falls inside this ball y. That is the whole idea. So, having said all these things, now it should be easy to observe that this element is actually inside this ball. Yes, why is it easy? So, norm of x dash minus y, that is what we wanted, to show that it is inside the ball, which is equal to norm of r x upon 2 times norm x, which will tell us that this is going to be just r by 2, which is less than r. That is it, done. That tells us it is an easy computation which tells us that this element x dash belongs to y, in fact. So, this tells us that this x dash belongs to ball with center at y and radius r, which is contained in the interior of y, which in turn is contained in y. That is it, done, and we are done. So, we have produced an element x dash which belongs to y, but the way we have returned our x dash tells us that you can rewrite x in terms of x dash and y, x dash minus y into norm x times 2 by r. A simple observation, maybe it is worth observing that if x is 0, then there is nothing to verify. So, let me add here that it should be non-zero, that is the most important, otherwise you cannot divide by its norm, right. So, now observe that this x dash minus y, x dash, it is again inside y and y is also an element of y, and therefore, this x dash minus y is also inside y, and what you have remaining here, it is just a scalar, and therefore, this whole thing belongs to y, and we are done with what we want, right. So, these are the two things that we wanted to observe for subspaces. Let us go to the next way of construction, what is known as the direct sum. So, if you have two spaces x and y, so if x and y are non-linear spaces, then we are going to have a new subspace or a new non-linear space. Well, we know what this direct sum means. This by definition we know, in fact, we must have learned this from linear algebra. This will have all elements of the form x direct sum y, such that x in x and y comes from y. Well, some people they even write it as ordered pair x comma y, but in functional analysis this is going to be the standard notation. So, we will be using only this much x direct sum y, this is the way, right. Now, the question is about how to give a norm here. In fact, several norms are possible. So, I will define one, in fact, rather than putting it as d, I will put it as norm. So, now the norm of x direct sum y, this is defined as norm x plus norm y. Well, so why am I writing it as x and y? To distinguish that this x, the norm that you write here is the norm on x, and the norm that you write here is the norm on y. So, let me write it here, x direct sum y. So, this is the norm on the direct sum. So, some people they even call this as the one norm on the direct sum, just like how you have one norm, p norm and sup norm. You can also do all these things even in the context of direct sums. You will have a large class of norms on the direct sum. So, let me just write down here. I will not go into the details and I will not go into the proofs, because the same proof whatever we did there in the last one, the same thing works and you should be able to work out the details. it is the, well, I should say it is the norm of the ordered pair norm x norm y considered as an element of C 2, considered as an element of C 2 with the P norm, that is it, right. So, with this you should be able to work out further details. So, in fact, so for 1 less than or equal to P less than or equal to infinity, one should be able to work out all the details, right. So, before we wind up this lecture, let me introduce one more concept, what is known as the quotient. Right. The next one is quotient norm linear space. So, what is this quotient? So, you have X is a norm linear space and Y is a closed subspace, right. Now, you have X mod Y, this by definition is going to be all elements of the form x plus capital Y such that x and x. So, these are what are known as the set of all cosets. Cosets of y in x, right. So, this is what you have. So, what we wanted is a norm on this space, right. So, having introduced this one, we will introduce what is known as the norm on this. So, in the next lecture, we will introduce a norm on this quotient space, and then we will also see some properties of this quotient space, and apart from which we will also prove some more general properties of a norm linear space. So, you can send your feedback to the following email ID. Thank you.